Hello, everyone. In the following session, we're going to talk about the minor project, which is the engine block manufacturing. And this is a part of your requirement to do the subject for 8621 manufacturing engineering. So in the following session, we're going to discuss all the possible ways to make the engine block by the casting operation mainly. And then we're going to talk about the extra machining processes required to achieve the final shape of the part. So, in general, every designer needs to ask himself some of the questions before we're going to finalize our report. So, first we need to know what is it, what we're making, and also we need to understand the functioning of this product, of how does it work. One of the questions we're going to decide the cost of the product is how many do I need to make. Finally, the optimum design is about how long does it need to last. The product we're talking about today is the Vector two-stroke engine, and is a very popular Australian product which was running for the past 70 years. The actually company was purely Australian till 2008. It's been sold to an American firm which making uh, the grass mowers. Uh, One of the memories we had for the mowers in general, the vector mowers, was at the opening ceremony of the Sydney Olympic Games in the year 2000. So actually, the engine which were operating these mowers was the same one we are going to work on, which is the vector two-stroke engine. These are some of the image we got for the part we have in the lab. Multiple view of the part just to show you what are the details required to be in this part. So obviously, let's inspect the part. It's just a block. We call it the block because it's going to be the solid part. It's not the only non-moving part in the engine in general. The other parts like the starter, even the carburetor in the old cars, the cylinders, the shaft, everything is moving. This is a block. It's not moving. That's why they call it a block. Solid shape with two main details. Main details we have are, you can see that we have the cylinder bore here. We have the gas outlet on one side. We have the air mixture with the fuel from the other side. We have the seat for the crankshaft at the bottom. The piston will be moving inside and outside the cylinder part. These fans meant to provide the cooling operation for the engine block, especially because this engine block is air cooled. That means it's not going to have a water cooling system like the ordinary cars we have. More views around the top view of the engine block. The side view, this is the fuel air mixture inlet, and actually the carburetor will be sitting in this side. This is the rear view, and mainly we're going to have the output shaft will be sitting on this direction. I have the full assembled uh, engine in the lab, which I can use it later to illustrate the operation of the two-stroke engine. Now more details, and this will come mainly to show you what are the most critical points we are going to have in this engine block. For example, is going to be the location of these holes, which is going to be used to connect the engine block to the other parts of the engine, and also the quality of the seal location, the quality of the cylinder bore. Okay, it should be quite uh, good surface finishing, and we do it by an operation called the honing. This will be the bearing seat. So once again, we are going to have a critical dimension for this one, especially that the bearing is going to be fit in by using the press fitting operation. Just add a little bit force to uh, seat the bearings in this accumulator. So that's why just remember that these surfaces, one, two, and three here, are going to have very high tolerances, while the location of the holes and the flatness of these surfaces also going to play a big role to be sure that this engine is going to be working with very high efficiency. Actually, this image also can show you some of the details we have inside, which are going to be pretty in mind before you're going to do the casting operation. I just had this photo to show you what will be the shape or the silver softness we have for this part. So mainly, by looking at this surface, you'll say that this part has been made by the sand casting operation. The other details, like the internal cavities, the complicated shape for the fins, also going to tell you that this part has been made by an expandable casting operation. It's very hard to make such shape by using the die casting operation. I gave you a hint yesterday about how we can modify the shape of the part if you would like to make it with die casting operation. For the internal details, you don't have to worry about these details because usually the core is going to be the part that decide what will be the shape of the internal cavities. I'll try to show you a video of the die casting operation for the aluminum blocks. So these are some of the catalogs on for the full assembly of the engine and block for Vector. You can see that why we are going to need to have a very high tolerances for these parts, because you can see that the cylinder with the rings is going to be sitting inside the cylinder bore, and that's why that the tolerance between the rings and the cylinder bore should be very high. Otherwise, we are going to have either very tight uh, uh, movement between both, or we are going to have a loose contact, and thus we are going to have some of the pressure to be escaping from the engine while operating, and this will reduce the efficiency by a very huge amount. We said that on the other side, at the other end, we're going to have the bearing seat. So these are the rolling bearings or the ball bearings, and that's why we said that this diameters should be critical dimensions. Now, let's have a look to distinguish between the two-stroke engine and the four-stroke engine. So this is the principle of a two-stroke engine. Again, to have the crank connected to the piston. The piston is going to be moving upward and downward through the cylinder case. Now, during this operation, when the cylinder will go down due to the movement of the crankshaft, you will see that it's going to attract uh, the fuel to the chamber. Okay, then it's going to go up, compressing this fuel, and the spark will be provided. It will cause an expansion due to the high pressure, and this will push the cylinder down, and thus the exhaust gas will be leaving through the exhaust, which is going to be, of course, going to connect to a silencer. So this will be the movement. The difference between the two-stroke engine, which is older than the four-stroke engine, is that we don't have a moving valve. The valve or the exit and the input ports are going to be stationary. Again, in this part, the petrol air mixture, we're going to have the carburetor connected to decide what will be the amount of the fuel to be mixed with the air and sent to the engine. So this is different between the two-stroke engine to the left and the four-stroke engine to the right. We can see that in the four-stroke engine, we're going to have the two moving valve, and this will simply going to add the extra two strokes for the engine. Now, if I get to ask you about what the difference between this engine and the diesel engine, I would like you to write down some of the comments in your report. And actually, the many of the people will understand the difference very easy and can distinguish between the diesel engine and the petrol engine. So the task we would like to have in this session is to examine the Vector two-stroke engine and investigate how to fabricate the engine block. Each student individually need to organize his or her written project report by addressing the criteria that can be found in the marking criteria for the project report of the 48621 manufacturing engineering. It's available on the Canvas. You can find this one at the first module within the modules. The following information may be included in your report. First, introduction about the product, something similar to the one I just mentioned, the advantage and disadvantage. Also, the type of the material and the casting method used for the engine block and the alternative options. Okay, so we said about the type of the material, and we need to add the alternative material can be used, casting method used, and the alternative casting method can be used. And of course, you need to give a brief discussion about why we choose this material. Three, a brief description of all the manufacturing processes used and the flow chart of these processes. The correct order of manufacturing operation with the reasons why you had this order. Identify the critical and non-critical parts of the engine block. I just mentioned that earlier. And some photos with dimension of the different views of the engine block. Next one. I'll try to make a session on how to sketch the engine block. You can follow this one and add your own engineering drawings. So what to hand on for this project? Each student need to submit an individual written report, and there is no strict limitation of the page number. But as a reference, 10 pages may be suggested if A4 paper is going to be used with normal margin, single line space, and using the Time Roman 12 font are going to be adopted. When you are going to finish this report, you need to submit it through the Canvas. When to submit is check the spreadsheet which is available on Canvas, will show you what will be the date of the submission for this report. Maybe it's going to be at the end of the week number 6, Sunday, 11:59 p.m. Now, let's have a full discussion about the engine block manufacturing processes. The following pages actually was one of the projects I was working at in 2011 in Sydney Uni, where we made an engine block for one of the old cars that we couldn't find the replacement for its engine. So first we need to go back about the introduction about the engine block. So that in the video I made to you earlier, I described the process of the engine block and what is the importance of the engine block. Is going to be a good idea actually to repeat that again. The cylinder block, which also called the engine block, is the main structure of the engine. So actually, when you open the engine hood in your car, you will see the engine block, and every other details is going to be above it. Inside is the heart of the car, how the car is going to work. The engine block is going to give a space for the cylinders. Some of the cars have 2 cylinders, some of the cars have 3, some of the cars have the 5, 6, 4, whatever the number is. The maximum number of the cylinders we have in one car is 12, but the 12 is normal in the trucks, for example. It's also necessary to give the passage for the coolant, which can be air or it can be water. Give the passage for the exhaust gas. After the explosion process, we need to release the gas inside the cylinders and intake gases to pass it over the engine and hose for the crankcase and the camshaft. The engine block is the main housing of the hundreds of the parts found in the modern engines, and is the largest among the engine parts, and it also constitutes something between 20 to 25% of the total weight of the engine. First successful internal combustion engine, which can be used in automobile, was built by Siegfried Marcus about year 1864. It was upright single cylinder with 2-stroke petrol engine, similar to the one we are going to discuss. The material used to build the engine block has been given the engine the highest strength with very low weight which is going to be more important for the power of the engine. Now, why we need to have very high strength? Because we said that inside the engine, we're going to have the explosion to be happen multiple times in every second while the car is driving. This explosion, that's mean we're going to have very high pressure inside and very high temperature. So our engine should withstand the changes in the temperature and not getting softer. And also it should withstand the forces resulted from the explosion pressure. At the same time, the weight is going to be very important. And that's why it's very hard to find any steel engine because the steel is going to be quite heavy. So that's why we tend to use a lighter material, which is going to have the same specification of the strength and the thermal stability. For many years, the engine block has been manufactured using the cast iron alloys, simply because the strength of the cast iron is quite high, and also the cast iron is quite low, and have some good wear resistance. But as the engine became more complicated, the engineers found new materials to reduce the weight, as well as to increase the strength and the wear resistance. In addition, is going to increase the heat transfer rate and keep the engine colder. The common alloy which widely being used nowadays is the aluminum alloy. It's more popular due to its low weight, but mostly within the petrol engine, because it's not going to be stable with the uh, diesel engine. Now, the only problem with the aluminum is the cost is quite high. So this is an example of the finished engine block. We are going to go through the process of the manufacturing of this engine. And as I told you, this is the engine we worked on it in Sydney unit to build. It's made of aluminum because we couldn't have the furnace to melt the cast iron. The functional requirement of the engine block are, as the engine block is going to be the main housing of the engine, it has to include number of the requirements. This requirement will include the wind resistance, long lasting, low maintenance, and should withstand the pressure created when the combustion is going to take place. Also has to withstand the high temperature, vibration when the engine is going to be running uh, in the running conditions. You know that the engine is going to vibrate. I don't want my system to fail during the operation. For many of the requirements, the main feature is going to be the material we're going to use to make the engine. Now, the material used in the engine block casting are, in order to meet the requirements, the material used in the manufacturing of the product should contain many properties. They are, the material should contain high strength, good modulus of elasticity, very good wear resistance, and the ability to withstand the vibration and the corrosion resistance. The high strength is mostly going to be concerned in the diesel engine because their high compression ratio compared to the petrol engine. Now, the diesel engine doesn't have the spark plug, so it's count on the high compression pressure we're going to have inside the cylinder. The higher pressure will increase the temperature and make the fuel ignite and explode. So the material also should have a low density to reduce its weight, but with higher strength. So that's what we call it the weight to strength ratio. We're always going to look about this factor whenever we're going to design something. It should also have a low thermal expansion, so it's not going to be expand when the temperature is going to be high. And also should have good thermal conductivity, so it's going to release the temperature and keep the engine cool as much as we can. When it comes to manufacturing processes, the material should have a good machinability and good castability to reduce the time and the cost consumed in these two operations. So I don't want to have a titanium to make the engine block because it's going to be very hard to get machined and it's going to have very high melting temperature. As if the material is going to be too hard, the time and the cost of the manufacturing will simply going to be increasing, and this will increase the cost for these two operations. When the engine is going to be running, is going to be in running conditions, it generates the high vibration due to the motion in the internal parts, like the crankshaft and the pistons, and therefore the material has to be able to absorb the vibration energy without any fracturing. So based on the above features, the most widely used materials are going to be the cast iron and the aluminum alloys to manufacture the cylinder block. Now, the cast iron are used because they contain a good mechanical properties, have very good acceptable low cost, and the available compared to the other metals. It's just iron mixed with other compounding material like the carbon and the silica. But certain aluminum alloys contain most of the characteristics of the cast iron, but with lower weight. So most of the sport cars are going to contain the aluminum uh, engine block. Then the same thing going for the motorcycles, where the weight is going to be an issue. And also the aluminum alloy casted engine block give a good surface finishing and high machinability compared to the cast iron alloys. As the technology continues increases, the engineers has found a new material such as the graphite cast iron, which is going to be lighter and stronger than the gray cast iron mentioned above. And also the cost is going to be quite acceptable. So let's start with the material number one we are going to work at, which is the gray cast iron. Now, let me give you a hint. The engine block we're dealing with is actually was made from the gray cast iron. The gray cast iron is the first and the most material used in the manufacturing of the engine block. Though that the aluminium alloys also contain many similarity with the low weight and is still used in the manufacturing of the diesel engine block because of the internal stresses are going to be higher. The gray cast iron contains something between 2.5 to 4% of the carbon, 1% to 3% of the silicon. Other added materials like the manganese, 0.2 to 1%, 0.02 to 0.25% of the sulfur, and 0.02 to 1% of the phosphor. So you can see that the main components we're going to have is going to be the carbon and the silicon. 95% is going to be an iron. It has excellent damping absorptions, good wear and thermal resistance, and it's easily machinable and less cost due to its availability. Now, starting from the 1980s, the aluminium introduced itself as an alternative for the gray cast iron. Its main feature was the low weight, and it thus is going to reduce the weight of the engine as well as the vehicle in general. But the main disadvantage is the cost compared to the gray cast iron, because the aluminium is quite precious material. The aluminum alloy has good machinability, softer than the gray cast iron, and there are two aluminum alloys that are mainly used in the manufacturing of the engine blocks, which are the ingot A319 and the ingot A356. The 319 aluminum alloy contain 85% to 91% of the aluminum, 5.5 to 6.5 of the silicon, 3 to 4% of the copper, 0.35% of nickel, and 0.25% of the titanium, plus the iron by 1%, manganese 0.5%, and 0.1% of the magnesium, and finally 1% of the zinc. The main good advantage of this alloy is the good casting features. It's going to have very high corrosion resistance due to the presence of the manganese and the zinc, magnesium and the zinc, magnesium and the zinc, of course, and it have good thermal conductivity under the heat treatment of the T5 processes. It's going to generate high strength and good rigidity for the engine block, which is going to be somehow close to the gray cast iron, but it's going to be, of course, less than gray cast iron. The A356 contain 91% to 93% of the aluminum. So you can see it's going to be less. The silicon percentage will be increasing. The copper is going to be less. The magnesium is going to be increasing, and the other one is almost going to be the same amount. Although the mechanical properties are going to be similar to 319, where it's going to be under the heat treatment process, the T6 will gain the higher strength than the 319, but has lower modulus of elasticity than the 319 modulus of elasticity, and this will make it less desirable by the designers. Now, the other type of the material we can use is what we call the compacted graphite cast iron. Now, actually, this is the type we talked about in the lecture yesterday, that when it's going to be cooled down, it's actually tend to expand instead of contract. So compacted graphite cast iron has the higher tensile strength and modulus of elasticity compared with the gray cast iron, and it's due to the compact graphite found in the microstructure of the compacted graphite cast iron. The Similar to the gray cast iron, it has a good damping absorptions and good thermal conduction, but the problem is it has lower machinability and has limited life in its usage. Now, tooling required for the casting of the engine block. Now, in this session, we are going to be talking mainly about well, in this operation we made earlier, we use the sand casting. So to make the sand casting, what we need mainly is going to be the mold. Without the mold, we cannot do anything. So the main tool needed for the sand casting is going to be the mold. The mold is generated by the mixture of the sand, clay, and the water. So the water is going to moisture the clay, and the clay is going to work as the bonding material between the particles of the sand. The pattern is going to be the main tool required to form the mold cavity, as normally going to be machined by wood or aluminium, which can be easily machined. Sometimes we machine it with the plastic. Now I'm talking about the sand casting operation. I'm not talking about any loose pattern operation now. The pattern is going to be kept on the wood or the metal frame, and the sand mixture is going to be poured over it. Then the vibration are going to be applied for the mixture to get free from the air bubbles, and after the mold has been hardened, it can be used for the casting process. After the casting process is over, the casted engine block is going to be passed through a few machines to get the surface finishing and the correct dimensions. We can use the CNC milling machine and the boring machines to do these operations: the surface finishing, the leveling of some of the surfaces, drilling, tapping, boring. Okay, honing operation also can be used. So the manufacturing of the engine block are mainly done using the sand casting, although the die casting also can be used, which is going to be more cost effective as the die is going to be out easily due to the high temperature of the molten metals. Now, the high temperature of the molten metal will damage the die casting mold, but we have to use the die casting operation to mainly casting a lower melting temperature metals. You have to put that in your consideration. The casted engine block is then going to be machined to get the surface finishing and the cooling passages. And the sand casting process, the widely used in the engine block casting, is going to be what we call it, the green sand mold casting. When I say it's going to be green sand mold casting, that means that the mold is going to be wet. That's what we call it, green. The term green denotes to the presence of the moisture in the sand mold, and a combination of the silica, sand, clay, and the water are going to be poured into one half of the aluminum block pattern with the wood or metal frame, what we call the flask. The mold is then going to be compacted by applying pressure or vibrating on the metal frame, and this process is going to be repeated for the other half of the mold You remember we call it the cop and drag, and then both have again to be removed from the pattern. So this is the drag, this is the drop. Okay, within them we're going to have, if we're going to put them together, we're going to have the full shape of the engine. This is the wooden pattern. You can see that the wooden pattern is mainly going to show, going to represent the outside features of the engine block. If I get to compact these two sides and fill with the molten metal, I'm going to have the solid engine block. No internal details are going to be presented. Oh, by the way, this is, we have two halves here. One is going to do each side of the mold, drag and the drop. We take them out. We're going to have these details, and then we're going to uh, compact them together. Now, this one was dried, and this will replace the process of adding the metal jacket to protect the part from failing. Now we need to prepare the parts which are going to generate the internal cavities of the engine block, and that's what we call it the cores. So you can see that actually all these cores were made from sand. The location here, this will be for the oil pump. These are to make the cylinders cavity, and the black one is to make the water passages. Now, this one was actually painted with this black material, is only to prevent that these sand particles are going to be stuck inside the engine block, because this will increase the rate of the corrosion inside the engine block water passages. The main molds mainly going to be by adding all the parts together to make it as one cube. Now the mold is ready for the casting operation. The molten metal is going to be poured into the mold through the smaller front center holes, as you can see here, 1, 2, 3, 4, 5, 6, 7, 8 holes. Here we are going to have some of the air, you can see here, and these 8 points is going to be the inlet for the metals, and we have some vents to prevent the turbulences of the molten metal inside. So we said that we are going to pour the metal in the mold through the smaller front center holes, which fills the mold from the bottom back up to the top through the razors, which can be seen as the 8 large holes on the side. When the casting is going to be cooled down, the molten metal is and the razor is going to be drawn back down to the casting, and the razor will act as the main part of the casting process by supplying the required molten metals during the shrinkage process. So as we pour in the metal, it's cooled down, start to lose some volume. The molten metal in the razor will replace this shrink volume. So after we finish that, we just expand the mold, and we take the engine block out. So the cause inside the engine block has been removed by the vibration process. It's adding the vibration, and this will cause uh, the core sand to actually separate it from each other and destroy it, and then we can take it out. And then we're going to use the air blower to clean the engine flow cavities by 100%. So the rough aluminum block casting is going to be shown above after the removal of the sand mold. It's going to clean to look like that. The sand is going to be removed by applying the vibrating on the casting, and the casting has to be machined to get the correct dimensions and the smooth surfaces of the engine block. This is an example for one of the operations, which is going to be mainly about drilling the holes on the side. The theory about the casting. Oh, by the way, let me explain something to you. For this side, we did the milling operation. For the cylinder uh, hole, we do the reaming operation, which is increase the diameter to a certain amount. Then we're doing the honing operation to get the good surface finishing. We need to do multiple of the drilling and the tap operation to provide the holes with the internal thread on them. Theory behind the casting is this part is from the lecture number 4. The casting is solidifying process, which means that the solidification phenomenon controls the most of the properties of the casting. And most of the casting defects occurs during the solidification, and solidification occurs in 2 steps, which are going to be the nucleation and the crystal growth. In nucleation stage, the solid particles are going to be formed within the liquid, and these solid particles have a lower internal energy than the surrounded liquid. And therefore, they will go below the freezing temperature because of the extra energy required. And then again, it's going to get heated up to form the crystal structure. Some of the quality consideration we need to worry about during the production process are the strength of the sand had to be high to maintain the rigid shape. Otherwise, when I'm going to pour the metal, it will collapse. We need to have good permeability, which is going to be decided by the size of the sand grain. We said that the permeability is going to reduce the porosity of the mold, but is going to be but the lower permeability will let the process to have a good surface finishing. The thermal stability of the mold should be high to resist the damage such as the cracking due to the high temperature of the molten metal. The ability of the sand to compress during the solidification has to be high, unless that the casting will not going to be able to shrink freely in the mold and may result in the cracking. The sand has to be reusable for the next sand molding to be formed, because one sand mold can be only used once. The sand mixture must be well compressed around the pattern to get the high strength, unless it will be cracked during the casting or when the molds are going to be set on the top of each other. The razor has to be well planned to make sure that they're going to not going to be solidified until the whole block has been solidified. We just remember this point multiple times. The contains in the molten alloy must be up to the standards to overcome the defects. The clearance in the cylinder both the crank and the cam. Sorry, this is cam. Okay, the cam bearings has to be up to the correct standard measurements. The cooling grades has to be up to the standards, and the cooling grade mostly controlled by the molten metal and the surrounding temperature. Therefore, that the casting should be done in a certain thermal conditions. Now, what are the possible defects may happen during the production operation? And just remember that we need to reduce uh, these defects because any defects will reduce the strength of the engine block. As the engine block running under the higher temperature, small defects can be a reason for any failure on it. For example, a small bubble may cause a failure. Internal cracks may cause failure. So if the permeability of the sand used on the casting is going to be high, the strength and the surface finishing of the mold will be reduced. If the thermal stability of the sand is going to be low, the mold may crack due to the molten temperature, the molten metal temperature. If the compression of the sand is going to be low, the casting will not going to be able to shrink and will end up with a crack. If the razor gets solidified before the other parts of the casting, it will give the engine block with less strength and of course with less size as well. If the molten alloy is not going to be up to the standard, it will failure in the high running conditions. If the clearance in the cylinder both the crank and the cam bearings are not going to be up to the standard measurements, under running conditions, it may arise with the unwanted friction or loose. Now, two categories of the casting process we have in general. We have the expandable mold process and we have the permanent mold process. This is an example of the sand casting mold. We said it's going to be consist mainly of two halves, and we are going to have multiple parts which generating the internal cavity within the cast part, which we call the cores. We should have the razor, and the razor must be designed to be solidified in the final step. So it's going to solidify after that everything else is going to be solidified. Once again, to form the mold cavity in the sand casting, we're going to use a pattern. The pattern can be used made of plastic or wood or metal, and the pattern must be oversized. The core is going to be responsible for generating the internal cavity of the mold. That's how to make the patterns. We said we're going to actually machine from the wood or from the metal. Now, just remember that the pattern itself doesn't have any internal cavities, and we need to add the cores to generate these internal cavities. The gating system is very important, and actually it should be designed in very good way in order to provide the passage for the molten metal. So the molten metal will fill all the cavities within the mold before it's going to be solidified in the way. Also, it's wise to add some of the vent outlets, and this will prevent the, the compression of the gas that will resist of the filling of the mold cavities. The riser is a reservoir in the mold, which is going to be a source of the liquid metal to compensate for the shrinkage of the part during the solidification process. To pour the metal, we need to heat it to the melting point, and then we're going to add the heat of fusion, which is going to convert the whole solid to a liquid. It's not going to be enough. We need to add more temperature, more heat, sorry, to raise the molten metal to what we call it the boiling temperature. So again, to make it quite soluble to fill the cavities freely without any pre solidifying processes. To pour the molten metal, we need to care about the pouring temperature, the pouring rate, and the turbulences that may occur. Turbulences is some of the backflow that's try to resist the flow of the metal inside the cavity. So this photo show you the process of the transformation of the molten metal back into solid state. So you can see that the razors must be solidified after the solidification of the part. And all the way you can see that the solidification will start from the outside because it's going to be in contact with the walls to the inside, where it's going to have the temperature to be kept for a longer time. We have to remember that the pure elements is going to have different way of the melting and the solidification than the alloy. The alloy, because it consists of multiple metals, each one is going to have its own melting and solidification temperature. So we have to be sure, for example, that for the gray cast iron, we're going to have multiple metals. Each one is going to have a different melting temperature and multiple solidification temperature. So we are going to expect to have the slurry, which is a mixture of the liquid and the solid in multiple stage for every single metal we have in this alloy. It's a flowchart show you the sand casting process steps. We talked about this flowchart. You can use it directly, and you can reference that. We got this one from the reference book, and you can make your own for the whole process. When I say for the whole process is uh, after we doing the, you can actually add to this one is after the removal of the sand mold, cleaning and the inspection, we're going to have the finished casting. We're going to continue to do the machining process. the inspection process, and we are going to have the full engine block. So we talked about this one earlier. We're going to have the pattern. We're going to put in the box. We are going to compact it to make the track. Then we're going to repeat the same process at the top to make the cup. And then we are going to prepare the passing gates here. And then we're going to pour the molten metal, get the final part, trim all the braces and the flow gates, and get the product. Do some extra machining on it to get the good dimensioning and the dimensional specifications before we're going to have our part ready. The pattern the one we saw actually in the process of the engine block, the aluminum engine block was one of these types. We call it the cop and drag pattern. So we are going to have these two sides. We're going to put them inside the box, compact the material on the top of them, and we're going to have the two halves ready for to build the whole mold. The cause for the engine block is going to be a quite complicated shape, but once again, the cores are going to be made by parts, and then you can simply glue them to each other to make the more complicated shapes. To fix the core inside the cavity of the mold, we are going to use the chaplets. Chaplets mainly are going to be made of either low melting metal, or we can use the plastic, which is going to be evaporate and vanish. The core have something called the core boxes, which is going to be made used to make the compacting of the sand to a certain shape. Then we're going to bake it, and then we're going to glue them together to have the 3D shape. So you can see here that actually this was not made by one operation, but it was made by multiple parts that are glued together to make this complicated shape of the pattern. Now, alternative method for making the engine block is using the shell molding instead of the sand casting operation. This will be very popular, especially if you're going to make massive production. If I'm going to do one engine block, and this was actually verifying the question of how many I need. If I'm going to have the mass production of the engine blocks, then I can make the mold and make multiple shells, multiple cores, and I'm going to just put everything, the shell and the cores, into the supporting material in the box and start to pour the materials to have the finished part. Okay, so this is actually an example of making the engine block uh, by the shell casting. Okay, that's an example of part made by the shell casting. Now another process, if I would like to make thousands of the parts, I can do the operation by doing the loss form. So I have to make the pattern made of foam. I have to fill it with multiple uh, coats, and then I'm going to put it in the sandbox, and then I start to pour the metal to have the engine block ready for the machining and get the final shape. Okay, so this is the loss form operation. So what we have done so far was we explained the different methods to make the engine block, and I'm going to show you an example report during the lecture on Monday, and we are going to finalize this process of writing the report as soon as we can. I'll try to run an extra session for you after you're watching this video during this week. Probably it's going to be on Thursday. And then we're going to answer your questions regarding the casting processes for the engine block. Now, before I'm leaving, I'm going to try to find a video. Well, okay, I'm going to send a video for you on how to do the die casting operation for the engine blocks. Mainly it's going to be for the motorcycle engine blocks. Thank you very much for your listening and hope to see you soon. So be safe, take care, and bye bye.